Power is an English word, but in physics it has a very specific meaning. Power is, and you can underline this, the rate at which work is done. It's how fast energy is transformed from one type to another. Read, anytime we're talking about the rate at which something is done, we're dividing by time. Power is work over time. Callum, what would its units be? What are the units for work? What are the units for time? So power is measured in joules per second. Oh, I should say it's a scalar, has no direction, much like your futures. Except joule per second is such an important concept. Here's the horrible joke that I'm sure I used last year, Callum. Power is measured in watt. Help them out, folks. Power is measured in watt. Symbol capital W. And this already leads to an issue because in the equation, this W is work. In the answer, this W is watts, not west. And I think I've mentioned once or twice we need more letters in our English alphabet, so we're having to reuse them. And so just pay attention to the context. If you're expending energy, it's not how much work you do that makes you feel tired. It's how fast you do the work or how much power you generate. Power is what leads to tiredness. It's the difference between walking up a flight of stairs, Reed, and running up a flight of stairs. You're doing the same amount of work, but I know which one you're going to be huffing and puffing after. I could probably, every one of you at your young age, could probably walk 10 flights of stairs. You'd be tired at the end of it, but you could walk up a 10-story building. Probably none of you could sprint a 10-story building, 10 flights of stairs. You'd be doing the same amount of work, but you'd be doing it way faster. You're generating more power. Power is what makes you tired. So this is how stairs and other ramps work. You spend the same amount of work. In fact, it's MGH. But you take more time so you feel less fatigue. Example 1. A 60-kilogram girl runs up a flight of stairs in 3.32 meters high in 2.6 seconds. Nicole, what does A want me to find? So power is work over time. I need to figure out the work. When you climb a flight of stairs, when you're lifting your own body, what's the work done in lifting something? It's sort of on your formula sheet, although on your formula sheet, I didn't call it work. I called it something else. I think Maddie was the one who derived this earlier, but I'll see if you can remember it. What's the work done in lifting an object? It's on your formula sheet, but I didn't call it work. It's 3 letters. I called it P. What? Yeah, because it's also the stored energy that object has gained. So it's going to be mgh over time. It's going to be 60 times 9.8 times 3.32 all over 2.6. What do you get? I kind of contrived these numbers to give us an answer. Correct me if I'm wrong. You get 751, right? Isn't it? I think. Yeah, I did that on purpose. Oh, Nicole, power is measured in watt. The SI unit for power is watts, Pietro. The imperial unit for power, horsepower. 1 horsepower is 750 watts. You don't need to memorize that. If I do ask you to give me an answer in horsepower, I'll give you the conversion factor. But what's this girl's power output in horsepower? I contrived the numbers because it's almost, I can't type, Mr. Dueck, almost exactly 1 horsepower. 1 horsepower is 750 watts. She did 751. Just to give you some context, all of you have a mass around 60 kilograms, plus or minus. All of you weigh around the same amount as this girl. 3.32 meters, that's about the height of the stairwell back here. Could all of you run that in 2.6 seconds if you needed to, if it was an emergency? Yeah. All of you are capable of putting out about 1 horsepower for bursts. Now, again, if I asked you to run 10 consecutive flights of stairs like that, now the number really dwindles. Maybe if there's somebody here who's a really high caliber athlete in really good shape, they might be able to do it, but most of you aren't running 10 straight flights of stairs. So you can do 1 horsepower in bursts. The horsepower is a stupid unit. It was originally defined by James Watt, who, Reed, to me, is the most overrated scientist to have such an important unit named after him, the watt, because we also use it in electricity. If he had invented the steam engine, I would say name a unit after him, and many people think he invented the steam engine. He improved the steam engine. What he really was, Reza, was a good marketer, because he would go to farmers with his new and improved steam engines, and he would say, this engine has 4 horsepower. What does the farmer think? It does the same amount of work as? What a stupid unit. What kind of horses? The big Clydesdales from the Budweiser commercials? Thoroughbred on the racetrack? Small what? Because a horse is not a consistent unit of work. It's really a made-up unit, but the PR, the marketing was so good, Leo, we still use it. Engines measure their power in horsepower, despite the fact that none of you have grown up with horses, and none of your parents grew up with horses. We're probably 2 generations removed from most people, maybe 3 generations removed from most people growing up with a horse. So it's a nonsense unit. I wish they had named the watt after someone else, but I can't get that changed. Example 2. How long would it take a 5 horsepower motor to lift a 500 kilogram? You know what? We should underline the word lift. A 500 kilogram safe up to a window 30 meters above the ground. Paul, what's this question asking me to find? Time. What's that 5 power, measured in horsepower? Does the power equation have time in it by any chance? Does the power equation have time in it by any chance? Yeah, it does. I think I know where I'm going, but can I use horsepower? We're going to have to do a conversion. So I'm going to say to myself, P equals 5 HP, and then I want horsepower to cancel. Where do I want it to go in my conversion factor? On the? Yep. And just plain old watts on the, what is the conversion factor? Apparently 750 watts is 1 horsepower. So let's convert that power to watts. 5 times 750. 3750? Or am I off? Yes? 30, yes? So 3,750 watts. The rest of it, the 500 and the 30, I'll just leave there. I'll come back to it. Let's write our power equation. Paul, what did you say this question wants me to find? Where is the time right now? On the? Bleh. Wait a minute. I can times the time to the top on the left. How would I move the P over? So I think you're telling me time is going to be work divided by power. It's going to be, work. What word did I underline? Nicole, how do I find the work done in lifting an object? MGH, you say. So it's going to be 500 times 9.8 times 30 divided by 3750. This might work out to a nice decimal. I don't think you can get a repeating one. I can't do much more than that, but I don't think you're going to get a repeating one. 39.2. Anybody else? Chaz, I don't trust it. Yeah, got 2. Okay. Units, Paul. What if you need it done faster? You can't. You need to get a bigger motor. Now, this question here is kind of meh, because who really cares how fast the safe gets lifted up? But replace this with those big cranes and skyscrapers. It's actually a lovely calculus question because you're lifting a different amount of mass up a different distance each time as the floors get higher and higher. The first floor mass doesn't have to get lifted as high. The last floor mass gets lifted way higher. You can solve for calculus, and you can solve for T, and that'll be pretty accurate as to how long it's going to take you to get all the materials in place. And if you need it done faster, you need to get 2 cranes or a bigger crane. Okay, so this is used in industry. Example 3. Oh, no, I remember this now. Next page. Power is work over time, but work is what times what? So power is force times distance over time. Everybody write that down and then do me a favor, please. Circle the D and the T. Tayshawn, what are the units for distance? What are the units for time? What's meters per second a measure of? And speed, technically not velocity because we're in Scalarville. Another way to calculate power, power is a constant force times a constant speed. Did I give you that one on your formula sheet next to work over time? I can't remember. I'm mellowing in my old age, so maybe I gave it. Did I give it to you? I used to make my kids derive it because it's force times distance over meters per second. That's a speed. But apparently I'm nice. When do I use that one? Don't overcomplicate it. If they ask you for the power and they don't give you the time, but they give you a speed. Efficiency. Efficiency is how much bang we get for our buck. How much energy or work or power that we get out usefully as a percentage of how much we put in. It's expressed as a percentage. The Greek letter eta is used for efficiency. I used to use EFF as my abbrev for efficiency, and you may see that in some of my older answer keys that are online, Leo. I only realized or learned that eta was used about 5 or 6 years ago. So what does an eta look like? It looks like our lowercase n, but with a really droopy front leg. Well, it looks like I typed there. That's the Greek letter. What is efficiency? How do I calculate it? It's power out divided by power in. Or it's work out divided by work in. Or it's energy out divided by energy in. And then that will be a decimal to make it a percent. You multiply it by 100%. I don't memorize that. Here's what I know. Matt, in our universe, things can't be more than 100% efficient. I know it's always going to be less than 100%. Which means the smaller number has to be on top. The bigger number has to be on the bottom. Here's what I have memorized for efficiency. Did I give you this on your formula sheet? Wow, I used to make kids memorize this too. You were a jerk once, Mr. Dueck. Efficiency is going to be the smaller number divided by the bigger number, and then turn it into a percentage. We are not allowed to be more than 100% efficient. If you try telling me that something is 118% efficient, I will make fun of you in a nice loving teacher kind of way. Or if you're correct, I will grovel because in about 5 years, you'll be able to buy Elon Musk. You'll very quickly become the richest person on earth if you have a free energy source. But there isn't such a thing. There isn't such a thing. Brain is trying to remember what. Yes, this is what I was going to point out. The reason I get confused, Maddie, with out and in, there's going to be a question in about 3 units when we do circuitry, where it's going to give you a light bulb and it's going to explain what's going on. It's going to ask you for the efficiency. The problem is this. In our English language, the power in comes from, what do we call that? Outlet. And it's very easy to get the in and out confused. And I've lost track of how many times, Leo, I've had someone very confidently tell me on the quiz, oh, this light bulb is 140% efficient. No, it's not. No, it's not. It can't be. but I put the out in the, no, you did. Smaller number divided by bigger number. Please. I wrote efficiency is always less than 100% unless you're planning on winning a Nobel Prize. That's sarcasm. You won't find efficiency more than 100% because that would violate the law of conservation of energy. Okay. A typical household light bulb, the old incandescent ones, I'm going to have to retype this because many of you have moved to LEDs. The old incandescent ones, the ones that got really hot enough to burn you if you touched them when you were trying to change them, they transformed energy at a rate of 60 watts, that's 60 joules per second. But most of that electrical energy went into heat instead of light. So 57 joules per second was going into heat, only about 3 joules per second was going into light. If you have LED bulbs at your house, you'll notice you can touch them with your hand and not burn yourself. Oh, in fact, some of you might be old enough to remember a toy called an Easy Bake Oven, which was basically a light bulb oven that cooked from, I think it was a 120 watt light bulb in there. And that was enough to give you mushy brownies and you could claim they were cooked. Electric kettle transforms energy at 1500 watts. Basically, if it's an appliance, the more heat it moves around, the higher its wattage. In fact, all of you in your houses have 2 appliances that require a special plug, a 220 volt plug. Anybody know which 2 appliances are wired into your wall with this? It's a big, thick, round plug with a big, thick cord. You have 2 appliances. You might have more, but all of you have at least these 2. Which 2 appliances need special wiring? Because they move so much heat around. Think about it. Dryer. If you pull your dryer off the wall, look behind there, you'll see it's this round, weird-looking plug. It's a 240 or 220 volt outlet there. That's one. What else has a special plug if you pull it off the wall? Think kitchen. Stove, oven, yeah. That's moving so much heat around. Pull that one off and you'll see, oh, special plug. The third one you might have, if you have an EV, you might have a 220 volt fast charger in your garage. That would also have a big fat plug. Those are the big 3. Most of you probably don't have an electric water heater, and even if you do, those usually run off of 120 volts because they just slowly heat the water up. The idea is you keep enough hot water in the tank that you can add cold water and it gets heated up kind of quickly. Example 3, I like example 3. A 250 kilogram mass is lifted at constant speed. You know what? I would probably underline the phrase constant speed. I would probably also underline the phrase lifted. Sahib, what's A want me to find? Okay. That's going to be the work done in lifting. How do I calculate the work done in lifting? Yep. It's going to be 250 times 9.8 times 12.5. Yeah. How much work? 30625? Anybody else? Yeah. And I'm going to keep all of it for now because I have a feeling I'm going to use it. And that would be joules. Good. Tommaso, what's B want me to find? Power. Don't write this down. Don't write this down. Apparently I need to say this 3 times. Don't write this down. Look up. My first thought would be power is work over time. I just found the work. Do you see a time in seconds here anywhere? Huh. My second thought was, well, it's also force times speed. They didn't by chance give me a constant speed, did they? Okay. So which force? The lifting force. I don't know the lifting force, but let's visualize our free body diagram. We're not even going to draw it. We're going to try and do this in our head. Here's the mass with a dot. What are the forces acting on it? Get the obvious one. Okay. Which way is it accelerating? It's a trick question. Which way is it accelerating? It's a trick question. Which way is it what? It says constant speed. Which way is it moving? Okay, if it's constant speed, it means forces must be. I'm looking for a word that starts with letter B. Okay, so this is force lift. I don't know force lift. Oh, but look. I know the force the same size as force lift. Which one, if we're moving at a constant speed? So, I'm not saying that it is gravity because that's in the opposite direction and I would have to make this all negative. I'm saying it's the same size as the magnitude of gravity. That'll be calculated. It's going to be 250 times 9.8 times 2. Oh, is that going to be 409? No, 4,900, I think. Double check me. Yeah. Power is measured in watt. Watts power measured in? Watts? Okay. Matt, what's C want me to find? Okay, efficiency, it's going to be what we got out divided by what we got in, and I'm going with power because they gave me power in part C. It's going to be the smaller number divided by the bigger number. Now you might be tempted to say, Mr. Dueck, 10 is the smaller number, but it's kilowatts. 10 kilowatts. How many watts? 10,000. That's the bigger number. That's going to be on the bottom. It's going to be 10,000 on the bottom, 4,900 on the top, and then multiply that by 100 to get a percent. What do you get? I think it's going to be 49. Yeah. I need to change these numbers because, Reed, this is an electric motor. Usually electric motors are 80 to 90% efficient. I made up some bad numbers. If it was a gas motors in internal combustion engines, usually 10 to 20% efficient. Where does most of the energy for an internal combustion engine get lost to? Heat and sound, baby. You can hear one from kilometers away. That takes up everybody's energy. And yeah, they give off a fat ton of heat. From the page. A mass of 100 kilograms is pushed along the floor at a constant speed. I probably mentally underlined the phrase constant speed. If the coefficient of kinetic friction is 0.25, ooh. Maddie, what's this asking me to find? Do you think I'm going to use work over time or am I going to use force times speed and convince me? How do you know? No. How do I know it's force times speed? Yeah. And by the way, I'm pretty sure I can find the force. See, you were kind of right, but first of all, the reason I know don't go work over time, I don't see a time. I do see a speed. So the first thing I would go is I would say force times speed. Which force? You know what? There's a coefficient of friction. You know what this is going to be a good job for? Yes. A little delay there. What are the forces acting on it, Maddie? Get the obvious one. Are we thinking? Yeah. I think normal force the same size as mg, yes? Now, we're pushing, so there is an applied force, because it does say the mass is being pushed. Which force am I missing? Bigger, smaller, or the same size as F applied? How do I know? Why must it be the same size? Ah, there's so much information in here from Newton's laws. So going back to my equation, I would argue that power is going to be F applied times speed. I don't know F applied. Oh, but look. I know another force the same size as F applied. Which one? Okay, my next thought would be, hey, that's going to be the force of friction times speed. And I don't need to put a negative. It's not opposite directions. I'm just saying it's the same magnitude. Friction is what times what? Mu, I don't know the normal force. Oh, but look. So I'm going to get mu mg, there's my friction, and then times v. What's mu? I don't know. What's mu with you? 0.25 m 100 g 9.8 v 2. What'd you get? Power is measured in watt. Maddie, did the m cancel here? Be obvious. No. Maddie, power is tiredness. Would it be more tiring to push a heavier mass? Yeah, m better not cancel. Otherwise, somehow pushing a semi-truck would be just the same tiredness as pushing a little baby carriage. So that's good. That probably suggests at least I probably set this up right because it matches with the experience I've had in pushing stuff. Okay. No, I did this one with my other humans. Let me think through here what time we got. Okay, what I am going to do is I'm going to skip example 6. I'll do example 5. It says a person pulls on a lawnmower with a force of 25 newtons. It moves the mower 4.5 meters. The handle angle, maybe that's what I should call the angle from the angle, with is 15 degrees with the horizontal. U equals 0.1. You know what? I think before I even jump into this, this is going to be a good job for. Yeah, and also, do I see angles, everybody? Alrighty, I'm going to do my free body diagram over here. There's the lawnmower. Oh, this is going to be a lawnmower question, and it's going to be a lawnmower question with an actual lawnmower. What are the forces acting on it? Get the obvious one. Okay. Then we always, for lawnmower questions, we did the lawnmower part next. That's we called F applied usually. And there's going to be an angle of 15 degrees. And then read, I usually called this one Fx for horizontal, Fy for vertical, color, color, color. That's where the 15 degrees goes. Okay. Which force am I doing next? Normal force. Is the normal force going to be bigger, smaller, or the same size as mg? Convince me. Okay, Fy is doing some of the lifting, so the normal force has to cancel out a smaller amount of gravity. I'll make it stupid obvious. What else? Which way? I think so. And I think it's smaller. Honestly, I'm not sure, except I noticed that we started pushing on this and got it to move, which makes me think that we're pushing harder than friction is resisting. Okay. Boy, what does A want me to find? Keep reading. Because what's B want me to find? Yeah, so we better be specific. Work done by the person. You know what? I think this wants me to find the work done by the applied force. Well, work is what times what? Boy, work is not force times velocity. That might be power. Work is what times what from my formula sheet that I have in front of me, so I don't have to memorize these things. Okay. Folks, which force goes with the same direction as the distance in my free body diagram? I'll give you a hint. It's not F applied. Paul. Boy, you Fy sine. Which trig function is Fx? Of course it is, not just of course it is, because didn't I tell you that the best definition of work was force times distance cos theta. Yeah, it is cos. Because we said if you're pulling at an angle, that was the best definition of work. So let's crunch that. It's going to be F applied, which was 25. Distance 4.5. Cos 15. What's the work done on this object? How much energy was put into this system from the person? How much food energy did this person lose? What do you get, Race? Like, is it solar? Dead batteries? Died completely? Because that message would have been appearing on your screen for like a month and a half, I think, the dead battery warning. Really? Maybe they finally fixed the software. On the old TIs, the battery getting low battery warning would show up, and we would tell the kids, you got 3 months easy. I always felt that TI must have owned a battery company, a battery factory. It was just trying to get kids to put more of those batteries in. Maybe they find, or the algorithm was bad. Maybe the software got improved. So ignoring ERASA, because, you know, Leo, what'd you get? 108.7. Anybody else? Yep. I'll carry an extra sig fig or two, and that's going to be 109 if I go to 3 sig figs. Work. I'm going to be very careful. What's work measured in? I didn't say watts work measured in. What's work measured in? Joules. This is the one where it's very tempting because you just wrote W equals to put a W next to your units subconsciously. Okay. That's how much energy this person poured in to causing this lawnmower to speed up, but not all of it went into kinetic energy. Not all of it went into kinetic energy. Cesare, what's B want me to find? Work done by friction. You know what? That's going to be the heat, by the way. That's going to be the force of friction times distance. I got the distance, okay, 4.5. Friction. Friction is what times what? So this is going to be mu times the normal force times distance. I don't know the normal force. And I can't really say, oh, but look, another force same size as a normal force. I think I'm going to have to figure it out. Thankfully, I've got a free body diagram. Are we sinking into the ground like quicksand? Are we flying like Superman? What that means is everything down has to equal everything. What's everything down? I think the only thing that I have pointing down, I'll do this over here, is mg. Has to equal, what two things are pointing up? Matt, how would you get the normal force by itself? You do subtract. The normal force is going to be mg minus Fy. Boy, you Fy. So, okay. So you know what you can do if you want? You could go, that's going to be F applied sine theta. That's what's going to be over here. The work done by friction is going to be mu, and then in brackets, we'll have mg minus F applied sine theta times distance. Well, let's see. What's mu? I don't know. What's mu with you, Mr. Dueck? Mu is 0.1 m 20 times 9.8 minus 25 sine, no, not 25 in, Mr. Dueck, 25 sine Sine 15. Sine times distance, which I think is 4.5. I think. What do you get? Why did I? Is it negative 85.3 or 85.3? Is that what you got on your calculator? Why did I write it negative? Which way is the object moving? Which way is the force? They're in opposite directions. So you can either just say that, or you can say cosine of theta is 180, because you'll also get a negative 1. So what I should have done, had I really been paying attention, is right here, I would have said, you know what? It's going to be the opposite direction, the opposite direction, the opposite direction. What'd you get? Negative what? Yeah, 85.3. Is that what you're saying? I need some consensus is all. Is that yes? Okay. 85.3 units. That's got to be joules because it's work. In fact, that's how much energy we lost to heat. It's negative because it's an energy loss. The floor heated up. We're going to skip example 6. Oh, we're also going to skip the time, part C. We could do it. D is 4.5. A, you could find out. You do have to assume VI is 0. Not wild about that, but okay, it works. Example 8. On a stair climber at the gym, a 75 kilogram person lifts their center of mass 22 centimeters. Jeez, Dueck. 22 centimeters. How many meters? 0.22 meters. Divide by 100 is a shortcut. If they take 360 steps in 6 minutes. Jeez, Dueck. 6 minutes. How many seconds? 360? And their muscles are 180% efficient. 180%? 18% efficient. I didn't see the decimal for some reason. That seemed a little high. Can't have more efficiency than 100%. My brain was going, something's wrong. Then find, okay. Ooh. What's A asking me to find when it says the rate at which the person does work? Power. That's the rate at which you do work. Power. Am I going to use force times speed, or am I going to use work over time? How do I know work over time? Ah, they gave me a time. So it's going to be the work over time. There's another word I probably should have underlined, and it's the word lifts. If I'm lifting, what's the work? Okay, this is going to end up being mgh over time, where m, 75, g, 9.8, h is not 22 or 0.22. Because how many steps have you taken? How many times have you raised yourself that height? Same answer. So it's going to be 0.22 times 360, all divided by, what's the time? 360. Oh! Is there a 360 on the top? Is there a 360 on the bottom? Is there a 360 in every single term? Then Leo, by a wonderful coincidence, yay! How many joules of energy have I burned doing this stair climber? What'd you get? Yeah, type it into your calculator. What'd you get? You're writing and then typing, right? Maddie, you got an answer? What'd you get? 161.7. Anybody else? Yeah? Units? What?
Watts.
What?
Watts.
Okay. Raisa, what's B you want me to find? Power. Didn't we just find power? I guess this must be a different power. What haven't we used yet? The efficiency. You know what I might do? I might write down my efficiency equation, which says that's power out divided by power in. That 161.7, Raisa, is that the power we got out at the end of this exercise, or is that the power we put in before we started exercising? Yes, it is. That's a tricky part to get. So, what do they want me to find? Efficiency is 0.18, because they told me. Next. I think they want me to figure out. So the power this person put out was 161.7 joules. That's 161.7 joules per second. They're actually burning more than that by a long shot. Where is a lot of the energy being lost as? Think about when you exercise. What happens to your body? Heat. Yeah. Okay. So you ready? We want to get this by itself. Where is that right now? On the, I think we'll multiply it to the top and we'll divide the efficiency down. The power in is going to be the power out divided by the efficiency. It's going to be 161.7 divided by 0.18. This person, by lifting their body, is putting out 161.7 joules of energy every second. Not how much they're burning. They're burning more. What? What'd you get? Oh, that's right. I keep picking on you, forgetting about that. Nicole, what'd you get? I can't hear. Sorry? 898. Anybody else? Units? Okay, so just a little nerd physics and a Captain Obvious physics, I hope. If you're in better shape so that your body is more efficient, if this number gets bigger because you're more efficient, what happens to this number? Less tired. Or if you're in lousy shape, you're actually burning way more energy per second than someone who's in good shape to accomplish the same exercise. The other thing, and this always bugs me, if you go to a fitness place and they have any kind of an exercise machine, many of them will claim to tell you how many calories you've burned. They measure in calories, not in joules. First of all, does the M cancel here? Did the mass cancel? If they don't ask you to type in your mass in kilograms or in pounds, that number they give you, calories burned, is totally bogus. But even then, if they don't somehow know your internal metabolism and how efficient you are, their number that they're giving you is bogus. Don't think, oh, it says I burned 420 calories. I'm going to go have a 420 calorie snack and break even. That number is to give you a goal to set yourself for and to track. It is not accurate. Not a chance. They don't know nothing about me. What's your homework? I'm not going to assign any questions from this lesson. I'm not going to collect this yet lesson. You'll do homework on work and power on the ultimate review. Speaking of the ultimate review, can you get it out, please? It's the one that looked like this. Questions that I'm not wild about that you can probably get away with skipping. Those are all good. Okay, you know what? I'll do my I like this question routine with you guys. Let me go back to the beginning here. I like number two. I like number two. Number two is a nice question. I like number three. I'm probably going to ask you some kind of a units related question because we've done enough physics now that I can do it as a basic multiple choice. And if you haven't figured out, I obsess over units. I like example four. I like number four is good. 5 is good. 6 is good. 7 is good. 8 is good. I think I really like number 9 in that this is a graph of, there is going to be a written question with a force versus distance graph. Here they're asking you to find the mass, but they gave me the speed, or I'll give you the mass and say find the speed. It's the same approach. Same with number 10 is good. Although all number 10 is asking you to find is the kinetic energy, I would probably ask you to do something more, find the speed. 11 is good. 12 is good. I like number 13. Absolutely. 13 is great. And it's a roller coaster. You can cross out number 14 completely. I like 15. I like 15. I like 50. Oh, yeah. I really like 15 because part B, they're asking me to find a speed, and then they even stuck some efficiency in there. That's nice. I like number 16 is good. 17, meh. 18 is very tough. Maybe tied for the toughest question of the year. Look at my answer key and see if you can figure it out, or make up reasonable numbers and see if you can spot it. I'm not going to ask you one this tough, though. You can cross out number 19. 20 is good. You can cross out number 21. So it used to, on the old provincial, the very last question, you had to do some kind of a graph and then interpret the graph. I'm not emphasizing the graphing as much, so I'm cutting corners. 22 is good. You can skip 23. 24, 25, 26 are all good. I like 26 especially. 27 is good. 28 is good. 29 is good. 30 is good. 31 is good. 32 is good. 33 is good. 34 is good. 35 is good. You can skip 36. You can skip 36. You can skip 36. You can skip 38. You can skip 38. You can skip 38. What do you see in number 39? Did I say angle? I told you I wasn't going to give you one on your test, so I'll say if you want to skip that one, you can. If you want to try it just for giggles, because I did do an answer key for it, go ahead. You can skip number 40. For scholarship questions, both of these I say meh, not like last unit where I said there was 4 scholarship questions that I said were fair game. You can try them, but those are tougher than I'm going to ask you. Okay?